Hi, my name's Adam. I'm a first year PhD student at the University of Oxford. And today I'm going to be talking about characterizing batteries using nonlinear electrochemical impedance spectroscopy. I'm going to start by recapping EIS, talking about equivalent circuit models, and then expanding that to the nonlinear domain, and finally talking about some experimental results. So first of all, what is EIS? EIS is a general electrochemical technique used to measure the impedance of systems. I think it's best summed up by these 5 equations. So starting with number 1, we have the input into our electrochemical system. In this case, it's a sinusoidal current input. We then have equation 2, which is the output from the system. This is a DC voltage plus a sinusoidal voltage offset by some phase from the current. We then take the Fourier transform of these signals and arrive in the frequency domain with these 2 graphs. So both are similar, both have some noise floor, which is typically set by our experimental equipment, i.e. the equipment we use to record these signals, and you then see a peak at the fundamental frequency for both the current and the voltage. And then if you divide the frequency domain voltage and current, you arrive at the frequency dependent impedance of the system. If you then repeat that process at a number of frequencies, you will produce a graph similar to this one on the right. And this is a very characteristic electroimpedance spectroscopy graph, similar to one that you may have seen before. This graph can be broken down into a number of constituent components. So starting from the right, this is the low frequency side of the graph, and this is typically attributed to diffusion, as diffusion is a slow process, and so you tend to see it occur below 1 Hertz. As we move above 1 Hertz, we move into the charge transfer and solid electrolyte interface region. Between 1 Hertz and 1 kilohertz, these 2 phenomena dominate, and although I've drawn them as separate semicircles, often it's the case that these 2 processes collide with each other and aren't as easily separable. Above 1 kilohertz, what you tend to see is some inductive value, which often is attributed to an experimental setup error, i.e. inductance from loops of wire somewhere in your system. The whole graph is also offset by some value, which is the result of some kind of ohmic system. Typically, the circuit equivalent would be a resistor. Often when talking about EIS, equivalent circuit models are used to describe them. And so what I've done is I've taken the graph shown previously and broken it down into the equivalent circuit model. And again, each element is replaced by a circuit equivalent element. However, there's one that's not as common in circuits, and that is called a constant phase element. So typically, a constant phase element is described as an imperfect capacitor, because although batteries display capacitive behavior, they are far enough away from a perfect capacitor that a perfect capacitor just isn't a good model for it. And so the constant phase element models an imperfect capacitor by adding the little alpha subscript to its equation. So now I'm going to talk quickly about why the constant phase element is necessary. Alavi et al. Showed in their paper time domain fitting of battery electrochemical impedance models that a fractional model was a much better fit to true data when compared to a Randall's model, where the fractional model was using a constant phase element and the Randall's model was simply modeling a capacitor. and this was fitted to a reduced order equivalent circuit model shown on the right. So now I'd like to move on to nonlinear EIS. And to start with, we're going to go back to the original 5 equations and focus on the voltage frequency response. So traditionally in EIS, the idea is that you keep the current low enough as to not excite any nonlinear elements. And so this low current is really good because you can hide all of that. The problem with that is it's really quite small and it's often very far away from the operating point of these batteries. And so as you increase the current, what you see in the frequency response is peaks at the second and third harmonics of the system. And so 2 and 3 times the fundamental frequency. And so what nonlinear EIS tries to do is it tries to capture any information that might be stored in these second and third order peaks. And so to do that, we introduce a 6th equation, which is the voltage response at the second harmonic divided by the fundamental current squared. The reasoning for the squared in this equation is explained in the Murbach et al. Paper, which I'll discuss quickly later. And so what this lets us do is it lets us have a sort of quasi-impedance, which allows us to display the second and third harmonics in a way that is similar to the first, i.e. on a graph of real versus imaginary impedance. And so the shape of this graph can vary quite a lot. And unlike EIS, it's not quite yet tied down as to how the shape of this graph evolves versus all of the parameters that are in a battery. So now I'd like to talk about some experimental results. So the aforementioned Murbach et al. Paper was one of the first to have experimental data from nonlinear EIS. And what they showed was that they were actually highly instrumentally limited in that the signal to noise ratio above 10 Hertz was actually so great that their data from this region wasn't usable. But something else interesting that they showed was from their synthetic data generated by a model. They showed that by varying the positive electrode anodic transfer coefficient from 0.45 to 0.55, you see a significant change in the second harmonic as shown in the graph on the right. And this is really interesting because varying this parameter has no effect on traditional EIS. So to see it have an effect on the second order harmonic proves that there is information in there which you can't access with a traditional EIS setup. And to talk quickly now about some more experimental results from Harting et al. They showed that the magnitude of the voltage response from the second and third harmonics actually falls away as you increase the frequency. And so at lower frequencies then, the nonlinear elements are much more responsive, and at high frequencies, that behavior seems to die away somewhat. In my research, I'm developing a novel system for measuring nonlinear EIS over a much wider range of frequencies than seen in the literature. And together with our colleagues in maths, we are using this to accurately and quickly parameterize battery models. In particular, we can estimate parameters that are not accessible by any other methods. This is useful for improved fundamental understanding as well as battery management systems. Thanks very much for listening.